See that X, the two lines intersect where they make the pattern? And then we connect the 3 points. And what shape do they make, Aharon?
M.
That's not an M. Look at this shape. Tell me what shape this is. What shape is that orange shape?
What?
Is that a rectangle? What shape is that?
A triangle.
You're right. Could you see that triangle is like as if I turned A around, I turned it like this, and that this is now a new copy of A?
Yeah.
Yeah? Well, some people might. Why do you think it's like I turned A around R? I turned the triangle around this point in the middle and landed there. Do you see how that could have happened?
What if I
Very good. That's an excellent explanation, except I don't speak 4-year-old. You might think it is because if you go ahead and you reflect something twice around 2 points, it's like you switched everything over. Now, when you reflect a figure across a line, the original figure and its image share a line of symmetry, which we have called the line of reflection. Can you point to the line of reflection? Yep, you got it. When you reflect a figure across a line and then reflect a figure across another line, then that final image is a rotation of the original figure. So a reflection and a reflection make a rotation. Can you say reflection and reflection make rotation?
Reflection and make rotation.
Excellent! The center of rotation is the point where the two lines of reflection intersect, like right there. Can you say intersect? Say intersect.
Intersect.
Excellent. The angle of rotation is determined by the center of rotation. The angle of rotation is Now, the angle of rotation is determined by the connecting center of rotation to a pair of corresponding vertices. So like this point and the corresponding one right here.
That point.
Yep, that point to that point. And that angle, that's the angle of rotation. It's 210 degrees right here. So from here to here in a positive direction, or a negative 150 degrees if we gotta go in the clockwise direction.
Huh?
Exactly. Can you say symmetry?
Symmetry.
Symmetry. So the line of symmetry for a figure, if we have an isosceles triangle, it has at least two congruent sides. There's a line of symmetry right down the center for this triangle, which we can draw like so. And so when we look at symmetry is like this line we can reflect everything on to basically turn this into two congruent right triangles. This line of symmetry can be thought of as a reflection across itself that takes a triangle to itself. Every point on one side has a corresponding point on the other. And in particular, the line of symmetry is equidistant from all the corresponding pairs of points. Another way of thinking about line symmetry is a figure has line symmetry if there exist lines, a line or lines, such that the image of the figure when it reflective over the line itself. Which of these have multiple lines of symmetry? Hit pause and try for yourself. Using your compass as a straight edge, draw one line of symmetry on each figure that has at least one line of symmetry. Sketch any remaining lines of symmetry that exist. What do you need to do in order to justify a line of symmetry? Well, one way to justify a line of symmetry is that perpendicular bisector thing we did, where you took 2 points that are corresponding to each other and create overlapping circles with the same radius. Now, how can I be certain that I have found all lines of symmetry? One way to do that is there are only so many ways you could fold something. So you fold it all the different ways, and that way you check. Now, on the other hand, rotational symmetry is a non-trivial rotational symmetry of figure. Is a rotation of a plane that maps the figure back to itself, so that its rotation is greater than 0 but less than 360. 3 of the 4 polygons above have non-trivial rotational symmetry. Can you identify the polygon that does not have such symmetry? Why does this one not have some symmetry? This one, I could turn it around 180 degrees and it slides on top of itself. This I could also turn 180 degrees, and this as well. When we studied rotations 2 lessons ago, we looked at both a center of rotation and an angle of rotation. Identify the center of rotation of the equilateral triangle below and label it D. Let's see. how would we go about finding the center of rotation? Well, we need the point that's equidistant from all 3 points. So if I want to find the point that's equidistant from 2 points, I use a perpendicular bisector. So making a perpendicular bisector for B and A, I make 2 circles with congruent radii and mark their intersections. And right there, I'm going to very gently mark the dashed line. That's the perpendicular bisector in that direction. I can then repeat my process, finding the equidistant, the perpendicular bisector between, let's say, C and A. It doesn't have to be C and A. It can be any of the 2 points. Could use B and C as well. It's just C and A are the most convenient. And then marking my perpendicular bisector there from the 2 intersections. Very lightly. Where the 2 perpendicular bisectors intersect, that is the center of rotation for the equilateral triangle. Now, if I were to rotate this 120 degrees, like so, then I would take C to A and A to B and B to C. If I were to rotate it again, let's see, so A, C, B would become, A would move to here, B would move to here, and C would move to here. And if I rotated it again, A would move to here, B would move to here, and C would move to here. Each time rotating a third of the way. So by rotating ABC twice in a row is the same as rotating ABC once by 240 degrees. So from here to here and then from here to here. So rotating by 120 degrees twice is equivalent to 1 rotation by 240 degrees. Notice this is how we would write it in formal notation, where rotation around D, 120, of rotation around D of 120 of triangle ABC is the same as the rotation around D by 240 of ABC. In later lessons, we can see that this can be written more compactly just by kind of making this kind of a multiplication thing. Now, if we rotated it one more time, so everything moves another 100. So A would come back to here, B would come back to here. We've gone back to the original. So that means rotating this shape 120 degrees 3 times actually results in the original shape, which we would represent by saying the identity of ABC. That means right here that we have clarified that the identity of ABC is itself a rotation 3 times. That means this has 3-fold rotational symmetry. In class tomorrow, we're going to experiment drawing all the lines of symmetry, locating the centers of rotational symmetry, identifying them, and looking at them closely, both online and in person. Looking forward to working with you tomorrow. Take care and have a wonderful rest of your day.